Thank you. So my name is Kyle Booth, and today I'm going to be talking to you guys about constraint programming for multi-robot task allocation and scheduling. It's a little bit something different than we've been seeing over the past couple talks. This work is joint work with my supervisors, Professor Najat and Professor Beck, and this is an application track paper. So I want to start things off by saying that autonomous mobile robotics are changing the world as we know it. And I don't want to spoil the conclusion of the whole presentation, but I'm going to. And that conclusion is essentially that I believe, as a roboticist first, constraint programmer second, that CP actually has a really important role to play within autonomous mobile robotics going forward. Some of you may recognize this image. It's actually a warehouse, or they call them order fulfillment centers, at Amazon. And these little orange things on the bottom here are what are known as Kiva robots. And essentially what these things do is they facilitate the day-to-day operations of this warehouse, which is kind of interesting. So there's a couple people in this picture. They might not be there next year. These robots are slowly taking over the operation of these warehouses. One thing that astounded me when I read it was that Amazon currently uses in excess of 30,000 of these robots at 12 different distribution centers. And the centers that actually have these robots have experienced cost reductions of 12%, which is pretty attractive. So it's no surprise that a bunch of other companies are jumping in and trying to take their piece of the cake. So in the top left, again, we have Amazon. To the right, we have a new company called Locus Robotics. In the bottom left, we have a Canadian-owned and operated company called ClearPath Robotics that is coming up with their own autonomous material handling system. And then in the bottom right, there's another company called NAP Robotics. So essentially, the point I'm trying to make here is that autonomous order fulfillment is actually paving the way for mobile robotics in other applications. The application that we're particularly going to study in this work is a little bit different, and it's driven by a different trend. And this trend is the aging of the population within the world. So if we look at 1950, the population distribution, we can see that it's actually heavily skewed towards younger folk. Okay? If we take a moment and kind of travel through the years here, what we'll notice is that the distribution actually starts to flatten. So we see the number of young people as a percentage of the total population is going down, and essentially there are more older folk as a percentage of the total population. And while this isn't a bad thing at all, what it's going to do is it's going to increase the amount of pressure that our long-term care facilities, retirement home facilities, and whatnot need to withstand to deliver the same quality of care. So a recent area of research is social robotics for elderly care. And a nice review paper in 2012 basically states that this research field is about 10 years old now, and the goal is to alleviate workforce pressures. So it's an industry that already struggles to get good employees and to retain employees. So they're thinking if they can inject social robots into these situations to autonomously facilitate social tasks and these types of things, we can ultimately improve the level of care that we deliver for a population that is growing in that particular segment. This picture here is essentially a user engaged in what's called a telepresence activity. So the robot enters their room. They can have a Skype call with a family member, all in the comfort of their own personal room. And telepresence activities are actually one of the activities that we'll consider in our talk today. So traditional robotics, when you think about that, you think about maybe like an automotive assembly line with some arms doing some fancy things, but they're static, the environment is known. New robotics, they're mobile and they're interactive. They're interactive with people, interactive with other robots, and the environments are dynamic. And this has been enabled through developments in a number of areas. The one that we're going to focus on today is essentially the coordination aspect, task allocation and scheduling, which is a pretty, I guess, hot topic in constraint programming. The robotics literature didn't really care about this until about 2004 because multi-robot systems weren't even feasible till that point. So Gerke et al. Kind of took it upon himself to write a paper that formalized this study. So given a team of robots, a set of tasks, and some sort of cost function, we're looking to allocate tasks to robot resources such that we optimize this cost function. Now, this looks actually strikingly similar to classical scheduling problems, right? So if we just take robots and we call them machines, and we take tasks and we call them jobs, all of a sudden we have a scheduling problem. Unfortunately, the robotics literature is building the theory behind this stuff from the ground up. And one thing they're leaving out is constraint programming, which I'm not a huge fan of. So we really want to inject constraint programming into this conversation, and that's kind of one of the attempts of today. All right, so the contribution. So we hypothesized that CP can be useful for these types of problems. In this paper, we apply CP to the automated planning and scheduling of tasks within a real-world retirement home. We conduct a thorough investigation of symmetry-breaking constraints as well as group variable orderings. And then we also implement a time window-based large neighborhood search. Essentially, in real robotics applications, coming up with really good solutions fast is very, very important. And we think that constraint programming is a pretty decent approach for this type of thing. So in terms of our ongoing project at the University of Toronto, it's a fairly large project. There's been a number of papers published thus far on certain subcomponents of this project. But the goal is to essentially integrate this team of social robots within this retirement home, provide social and cognitive stimulation through the facilitation of two major task types. So there's bingo games, which we'll look a little bit more at later on, as well as telepresence sessions. And ultimately, we want to build a system of a multi-robot system that is capable of autonomously allocating, scheduling, and facilitating such activities throughout the day. So these robots shouldn't need help from anyone. All right, so let's put some graphics in there, a little bit less text. So we have four primary problem components. The first being the retirement home facility itself, second being the users. Then we have a set of available activities and tasks. And last but not least, we have our mobile robot team. They look kind of funny, but they're actually starting to sell robots that look like that, so that's why I put that there. At the start of the day, from the perspective of the multi-robot system, this is what the schedule for the retirement home users looks like. It looks pretty boring. Essentially what we have so far is we have the components of each user's personal calendar. So these are times that they can't actually be involved in any other tasks. So meal times, leisure times, etc. And our two robots here, their job is to come up with a schedule that makes the day a little bit more exciting for the users at the retirement home. In terms of components of the problem, so we have the facility of the retirement home. We have a set of locations. This includes a games room, a meal room, a room that the robots can actually go and recharge their battery, as well as personal rooms for each of the users. We know the distances between all of these locations, and as such, we can use this to calculate a transition time matrix that's unique to users and unique to robots. This is just a screenshot from some of the simulations that we run. That floor plan is actually a real-world retirement home floor plan in Toronto, Ontario. All right, so we have our users. We have a set of end users. Each of them has a daily calendar and identifies the periods that they don't want to be bothered during. So this is like lunch, dinner, personal time, etc. And we have an estimate of how quickly they move through the environment, as well as their personal room location. And then we have our robots, very similar. So a team of M robots. We know how fast they move. We know the lower and upper limits on their battery level. Battery level is a very important component to this problem. And we know energy consumption and replenishment rates for various tasks, as well as where they can go to recharge. So it's a fairly complex problem, as you're starting to realize. So in terms of tasks, these are kind of the guts of the problem, and these are the things that we're going to be doing with the residents to make their day more interesting. The biggest one we have is bingo games. So essentially, bingo games are facilitated by robots completely. They're optional. They're 60 minutes in length, and they're located in the games room. And users, if they're going to participate in a bingo game, have to be reminded that they're actually in a bingo game before the game starts. And so this is just kind of a quick clip. We have a robot at the University of Toronto that is able to facilitate full bingo games from start to finish. This is just a looping clip where the robot's actually gone up to an individual, told them, hey, you put the, whatever you call that, disc on the wrong spot, and you need to move it because that's not a legal move. So it has vision recognition and all these types of things. So yeah, that's kind of cool. The next two tasks we have are telepresence tasks as well as bingo game reminders. Telepresence, as I explained earlier, you do the whole Skype thing with your family. They're typically 30 minutes long, and they are in the personal room of the user. And then we have reminder activities. Again, they're optional. If a user is going to participate in a bingo game, they have to be reminded beforehand so they don't forget about it. And that's me. It's kind of neat being able to put a picture of yourself in a paper, but I'm getting reminded that I have a bingo game later that day. So robots have recharge tasks. Recharge tasks are fairly important. They're variable in length, and this allows a robot, if it's packed too much into its day, to essentially boost its energy level so that it can continue to make the day exciting. Essentially, robots need to go to the robot depot to recharge, and they can replenish their energy there. These are obviously optional. And the objective is the problem is, given a single-day planning horizon from 7 to 7, we're looking to maximize user bingo participation. And what we're going to do is we're going to break ties on equivalent schedules based on an energy consumption component. All right, so this is what a good schedule looks like. And this is actually a schedule that CP generated. So we can see that the day is all of a sudden looking a lot more exciting. The users have pretty packed schedules, and so do the robots. And we can see down here, essentially, that we also track the change in robot energy levels over time. Just to point out a few things. So obviously, we still have our meal times and our personal times, but now we have a bingo game that's being hosted by one of the robots, and it happens that all of the users are actually participating in this game. That's not necessary, but since they're all participating, they all need to be reminded beforehand, so they all have that M task at some point before the bingo game. And then we have the telepresence tasks. Each user has to have a mandatory single telepresence task per day, just in the way we've modeled the problem, and you'll see that they all have that. And you'll note that for each task on a user schedule, we have a corresponding task on one of the robot schedules, and only a single robot can facilitate a task. We can't have two robots trying to do that. And again, so there's some dynamics in the energy and whatnot. So this is actually produced by the constraint programming formulation that we came up with, and now we're going to get into that detail. So our CP model, in terms of variables, we extensively use interval variables that some of you might be familiar with. We have interval variables xij that are present if user UI participates in task j and absent otherwise. That's that optionality component. We have interval variables ykj, and these are essentially modeling the tasks on the robot schedules. And interval variables are defined by this convex interval that includes their start time domain values, as well as this bot item that it represents the optionality. But essentially it just looks like this, right? You're scheduling blocks. We also have another variable for energy consumption for the robots, and the way we do this is we use cumulative expressions. Cumulative expressions are really nice because essentially what they do is they sum up a bunch of individual contributions of interval variables. So we can essentially say that the contribution of an interval variable is its energy consumption or replenishment. And in such a way we can actually model energy consumption throughout the day as some stepwise function. All right, so here's our CP model. I'm just kidding, we'll unravel and get into a little bit more detail. So we have our objective function here, and the objective function is fairly similar. So we're maximizing the number of bingo games played by users, and again, we're going to do this kind of prioritized schedules that use a little bit less energy, or the recharging tasks, so fewer recharging tasks on the right-hand side there. Subject to three particular constraint sets. The first is task sequencing and synchronization. So essentially here we define a couple sets that basically amalgamate all the tasks that could potentially involve a particular user or robot, and then we're going to enforce a couple no overlap constraints, including transition times on those tasks. And these just ensure that for users and robots, none of the tasks are interfering temporally. We'll also have a synchronization component. So if we have a task involving a human-robot pair, as I've written there, we're going to say that if both of those tasks are actually present, then their start time differences have to be 0. So they have to start at the exact same time. So we're synchronizing the tasks that way. Okay, so our next constraint family is task presence and precedence. We'll just go through this real quick. So essentially what this constraint says is that user telepresences are required, and that only a single robot can facilitate them. The next constraint says that at most, one robot facilitates bingo games. Remember, bingo games are optional, so we don't need to facilitate them. And it also provides an upper bound on user participation, namely that a user can't actually play a bingo game that isn't facilitated. Here we ensure that reminder tasks happen before associated bingo games, and then we have a linking constraint between a robot's ability to facilitate a reminder and a user's participation in that reminder. And the last set of constraints that we haven't unwrapped here is robot energy constraints. So here we say that our robot energy variable is within the bounds defined by the battery capacity of the robot. And then we also have this cumulative expression portion, which essentially for each interval variable that robot has on its schedule, there's going to be an impact on the energy level of that robot, whether it be consumption or replenishment. And the impact actually has two components. So there's a task component, how much energy do I need to do that task, and how much energy do I actually need to get from my previous task to where I am now. So we're incorporating both travel energy expenditure as well as task energy expenditure. And then their variable length, so we just define the bounds of the variable length task at the bottom there. So here's our complete CP model. I think it might be one of the first CP models I've seen here, so there we go. As we continue on, so in robotics applications, we need high quality solutions quickly. And unfortunately, I ran a few experiments with default CP, and it wasn't working too well. So I thought, well, are there actual structural components to this problem that we can take advantage of? And And a natural way to do that is through variable ordering heuristics, right? So can I take a group of variables, instantiate values on them, and then solve the rest of the problem? And that's kind of what we're doing here. The expression at the bottom looks a little bit complicated, but essentially what we're talking about is in a single stage grouped variable ordering, I take a variable type, so say robot bingo game tasks, I give start times to all of them, either absent or a specific start time, and then I continue on with my optimization. And I hope that the problem has become a little bit simpler by doing that. In a double-stage variable ordering heuristic, I'll actually take two groups of variables. So I'll first instantiate robot bingo tasks, and then instantiate user bingo tasks, and then solve the remainder of their problem. And hopefully it became a little bit easier. So that's one strategy we use. So the intuition is essentially that instantiating certain task interval variables early in the search might lead to more rapid feasibility. And in the constraint here, I've just highlighted a portion in red. So if we give a start time to a particular YKJ variable, we note right away that it's going to actually have impact on the domain of the other variables in that constraint and hopefully make the remaining model a little bit easier. So through some just experimentation, we found that the best single group of variables to instantiate first was actually robot facilitation variables. And then for bingo games, so bingo games are nice big interval variables, and they have a lot of impact on the domains of other start times of other variables when you actually implement those first. And in terms of double stage, it looked like it was most beneficial to instantiate first user bingo game participation and then robot bingo game facilitation. The next strategy that we use is actually a time window based large neighborhood search. Probably running out of time here, but essentially what we do is we initialize a time window. The first one is 3 hours from 7 to 10 a.m. We solve for 60 seconds based on the best method from the grouped variable ordering to get a high quality incumbent solution. And then while we're not out of time, so in 5 minutes, essentially what we do is we unassign all of the variables that have start times within that time window. We fix everything else, and then we resolve that problem for 20 seconds. So essentially we're just kind of looking at smaller pieces of the problem and seeing if there's local improvements we can make via this large neighborhood search. We replace incumbents. If we don't find an improvement in that 20 seconds, we actually shift the window 1 hour to the right and continue on. All right, so some results. We have a number of scenarios. The scenarios are fairly simple. They just get larger in size, so more robots, more users. And we do 10 randomly generated instances for each one. They're random in the sense that we change the retirement home floor plan as well as the user calendars, just so we have some different parameters going on. So we actually formulate both CP and MIP models, but the MIP model really struggles to find even feasibility for pretty much all of the problems. So we're focusing on CP in this particular talk. And we use CP Optimizer to solve the model. In terms of performance evaluation, we're going to use mean relative error. Some of you might know this metric. Essentially what we do is we calculate an upper bound on our objective function using a relaxed version of the CP model, and then we compare solutions we find at certain time steps to that upper bound. So that's kind of the Coles notes of what's going on there. And so here for scenario 1, so this is our smallest scenario, these are our results. So at the bottom you can see we have runtime. So we look at 5 different runtime intervals, so 0.1 seconds, 1 second, 10, and so forth. On the y-axis we have mean relative error. And what we can see is the dark gray and the gray are actually just CP under default settings. One is with symmetry breaking, one is without. And we can see that symmetry breaking actually doesn't help us at all in this case. So we kind of throw that out as an idea. I didn't actually cover which constraints were included in the interest of time, but we found that symmetry breaking didn't really help. CP default actually gets vastly outperformed by the technique where we actually take the robot bingo game variables and instantiate those first. So that's our best performing technique so far. In the second plot, again for the first scenario, so the smallest instance, we compare the single stage variable ordering heuristic with the double stage variable ordering heuristic and then the LNS. And we find that because this problem is one of the smaller problems, we don't actually see any meaningful improvement. So to see meaningful improvement, we have to look at larger instances. And so we're looking at 2 robots, 10 users, all the way up to 4 robots, 25 users. Again, these values are mean relative errors, and we have our runtime intervals across the top there. And if you look at 300 seconds, you can see that the LNS approach, as well as the 2-stage variable instantiations, are actually outperforming the single-stage instantiation. So we are seeing some improvement with our modifications of the search. Conclusions. So this is the thing I want to hit home with, I guess, hardest. I really, really believe that CP can play a really key role in this rapidly growing field of autonomous robotics. And there's a ton of current research opportunity out there. When you do a Google Scholar on CP for robot task allocation, almost everything that comes back at you is either MIP or genetic algorithms or whatnot, so there's a lot of space for research here. So in this particular work, we apply CP to our retirement home application problem, and we investigate a number of techniques in order to improve the performance of our methods. And at the University of Toronto, we actually have robots running around solving constraint programs, and it's a pretty cool thing to be a part of. So I just wanted to say thank you, and if you're interested in more CP for robotics, I have a session tomorrow at 11:20. So thanks very much.
Thank you, Kyle. So we can